Hello. Good afternoon. Good morning, everyone. Again, this is time to start the last section, hot topics, in this conference. So we have four speakers. Let me introduce the first speaker, Professor Robert Moszynski from University of Warsaw. So join me in welcoming.
Okay, thank you. Well, thank you, Mr. Chairman, and let me thank the organizers for inviting me to this exciting meeting. And let me thank that at this major atomic physics conference, you decided to give a slot to molecules, and I hope to convince you that molecules are even more interesting than atoms. Well, actually, you will have two hot topics in one, with three common points. The first common point will be the ultra-cold strontium diatomic molecule. The second common point will be to show that molecules are very different from atoms and that you can observe a variety of phenomena that you cannot observe for atoms. And then the third will be the synergy between high-precision experiments and state-of-the-art ab initio calculations. So on the theory side, the work was done by my PhD students, Wojtek Skomorowski, who is now a Humboldt Fellow at the University of Kassel, and then by Iwona Majewska, who just joined the group. And nothing would happen without a precious collaboration with the Z-Lab. This is Columbia ultra-cold molecule team led by Tania Zalewiński, this young lady here. She is the boss of the group. And two people that contributed most to the work that I will present is Bart McGuire, who just left. He was a postdoc, who just left the Z-Lab, and Mickey McDonald, who unfortunately will leave the lab by the end of the month. Okay, I will start with the old experiments by the old experiment by Tania Zalewiński, the 2006 experiment, in which she photoassociated two strontium atoms. Well, the first photoassociation experiment dates back to 1998. This was by Pierre Pillet and the group of Orsay. This one was much more clever because she photoassociated two singlet S atoms to the intercombination line, which means that she looked at a spin-forbidden transition. This resulted in bound molecules which had lifetimes of the order of microseconds instead of nanoseconds in the case of pure singlet or triplet transitions. Now, if you look at the spectrum that she obtained, you see a very nice progression of vibrational lines. And I would like to draw your attention to the energy scale and to interatomic separations. So if you look at the energy scale, you see that these molecules are very loosely bound. So this is energy in megahertz. For those who are familiar with wave numbers, well, the least bound state is bound by 0.3 megahertz, which is 10 to the minus 5 wave numbers, which is 10 to the minus 10 Hartree. And those who like electron volts, this is of the order of nano electron volt. So you see that this molecule is extremely loosely bound. And now look at the interatomic separations in these molecules. And it's unbelievable because this least bound state, in this least bound state, the two atoms are 500 Bohr apart. Okay? So just to tell you that in typical molecules, like the hydrogen molecule, the interatomic distance is 1.4 Bohr. In typical hydrocarbons, it's about 2 Bohr. So this is quite atypical chemical bond. And one may ask the question whether this is still a molecule or this is just a loosely bound pair of atoms. So just to continue on this point, let's have a look what is the difference between a molecule and an atom from the fundamental quantum mechanical point of view. And it turns out that if you neglect electroweak interactions, there is no difference between an atom and a molecule. Just both the atom and the molecule are described by 3 sets of quantum number: the total angular momentum J, its projection on the Z space-fixed axis, and then the parity P with respect to the inversion of the parity P. Okay, and then if you look at the selection rules for the optical transitions, well, we take the wave function of the initial state, of the final state, and the transition operator. And these selection rules are the same for atoms and for molecules, which means that we have electric dipole transitions which connect even and odd parity states. Then we have magnetic dipole M1, which connect even parity states. And we have E2 electric quadrupole transition, which also connect even to even. Okay? So when we treat molecules, it is customary to introduce what is called the Born-Oppenheimer approximation. And in this approximation, we just say that the total wave function of the molecule is factorized into the product of the electronic wave function times the wave function that describes the nuclear motions. Okay? Just look that this electronic wave function does depend only parametrically on the distance between atoms in the molecule. And this means that the electronic wave function does not have a definite angular momentum. It doesn't have definite parity, just because in the electronic wave function, the geometry of the molecule is frozen. So not all coordinates are treated on the same footing. So we have some additional symmetries which are related to the point group of the molecule. And you have heard that we have sigma states, pi states, and then if the molecule is homonuclear, then we have Gerade states or ungerade states. So how the selection rules look like in the Born-Oppenheimer approximation. So we do it in 2 steps. So first we do the integration over the electronic coordinates, okay? And then we do the integration over the nuclear coordinates. Now, if you have a loosely bound molecule, you can imagine that the wave function for a loosely bound molecule must be quite similar to the product of the atomic wave function, except that we have to take care of the Pauli principle, so we have to anti-symmetrize this product. And one can prove that the distance between the exact electronic wave function and this anti-symmetrized product of the atomic wave function vanishes as the inverse cube of the distance. If you take 500 cube inverse, that's a small number. You agree? So now one may ask the following: if this electronic transition moment that appears here, is it related somehow to the atomic transition moment? One would expect that if you have 2 atoms that are very far apart, so in fact they are very close to the asymptote, it may be so that this electronic transition moment is just proportional to the atomic one. Okay, so well, this is just a cartoon showing that if you have a ground state molecule, it vibrates very slowly. Then when we add a few quanta of vibrations, then the vibrational motion becomes very fast. And then we have atomic pairs. And the question is there a difference between this fastly vibrating molecule and the atom pair? And it turns out that, there is a difference in some cases, and in some cases there's no. And I will introduce the definition of superradiant and subradiant states. And we will call superradiant states those for which the electronic transition moment is proportional to the atomic transition moment. And then subradiant are such that the atomic transition is strictly forbidden, still the molecular transition is allowed. Okay? And this is illustrated here. So if the decay for atoms is gamma, in the case of superradiant is 2 gamma. Okay, now in the case of subradiant, the decay is not allowed via the E1 mechanism. So what can be the mechanism? Of course, it must be M1 or E2, because I told you that there is no difference in the selection rules for atoms and molecules. But what is interesting is that in this case, the atomic transition is strictly forbidden. Still, the molecular transitions are allowed, and they are purely molecular. Okay, and well, now comes the experiment. I was contacted by Tania Zalewiński in 2014, and well, they reported some new raw vibrational levels in the energy range from 7 to 5,000 megahertz. And we knew for sure that these cannot be Angerade levels because we knew everything about the Angerade manifold. Well, these levels were quite peculiar just because the spectral lines had transition strengths about 1,000 times smaller than for any other transitions. So then, well, we made a conjecture that maybe these newly observed transitions are strongly doubly forbidden transitions from the Gerade to Gerade manifold and from singlet to triplet. But if so, we know from the works of Herzberg that these are extremely weak transitions, so the lifetimes are very long, and in the experiment they observed relatively short lifetimes. So these are the questions that we had to solve. So what quantum chemists do in general, well, they compute all the potential energy curves, the couplings, and so on. They generate raw vibrational levels, and that's what we got. So I think that the first was 316 that they observed, and we did the calculations. This is in megahertz, and we got 315. Bingo. So then, of course, experimentalists, they ask, okay, tell us where are other levels. So then I think we started to look at other levels, and each time you see that the agreement between theory and experiment is excellent. I recall you that all these numbers are in megahertz. So there is a good agreement between pure theoretical predictions and experimental data, and this was the first result that supported that these are what they observed are these doubly forbidden transitions. But then we started to look at, because they can measure linear and quadratic Zeeman splitting, so we started to look at them. And here again, if you look at the numbers, linear, perfect agreement, quadratic, perfect agreement. So, well, this was the this was the proof that the observed transitions are really Gerade to Gerade, singlet to triplet. So now we had to understand what's going on, just because we know that the ratio of the Einstein coefficients is proportional to the square of the fine structure constant, which is 5 times 10 to the minus 5. But in the case of strontium, the line strengths were one order of magnitude larger. So you had to find an explanation why does it happen. And it happens so that in 2006, I published a paper with Béatrice Bustry-Envaux, who is now in Dijon. And we could prove that for some selected molecular transitions, the transition moment is proportional to the interatomic distance. It diverges with the interatomic distance. And if you make a naive estimate by using this result, okay, then we get that in the case of strontium, we get indeed one order of magnitude stronger life strength than expected from this ratio. Okay, but well, as you know, no, you may not know, but I am a quantum chemist, so quantum chemists usually do precise calculations. And when we did precise calculations, this is a kind of agreement that we got for the transition strengths. So the agreement is perfect. But then we had to go further and understand why the lifetimes, these are the line strengths, and the lifetime is usually inversely proportional to the line strengths. So why the lifetimes all of a sudden were much shorter than expected from the line strengths. And it turned out that even though we are in the asymptotic region, there is a coupling mechanism between two electronic states, which is of purely short-range character. And actually, if we include this coupling mechanism, you see that we get a perfect agreement between theory and experiment. So this is the radiative lifetime. You see that it's quite long, and this is including the predissociation mechanism due to the coupling between two electronic states. And this is how theory could explain all the experimental findings of the experiment. Now I briefly go to the second subject of my talk, and this is something that you could have seen on the poster number 51 of Mickey McDonald on the first poster session, is the photofragmentation of the strontium molecule from preselected Zeeman sublevel. So what they did experimentally, they produced an excited state revibrational level. They applied laser field, and then they photodissociated the molecule into two atoms. So in general, the photodissociation theory is based on the semi-classical model introduced by Zer and Bernstein in the late 60s and by Zer in the beginning of the 70s. And well, the photofragmentation is characterized by this kind of function, where we have theta and phi that are fixed and defined with respect to the quantization axis. And then we have chi, which is the polar angle defined with respect to the orientation of the polarization of the photodissociating laser. From the quantum mechanical point of view, the photofragmentation cross-section is defined just by the Fermi-Golden rule as given here. Now, if you look at the results, well, you will immediately observe that in some cases you have a perfect agreement between the semi-classical theory, and in some other cases, strong disagreement. So here you have quantum mechanical, here you have quasi-classical, and this is the projection of the Newton sphere. So we had to understand it, and actually the understanding is that if you fix the Zeeman sublevel, and they were clever enough in the experiment to do it, then all of a sudden well, you get very unusual features in the photofragmentation cross-sections that cannot be explained by the semi-classical theory of Zer, but still they can be quantitatively explained by the full quantum mechanical model. And well, this is a very clever experimental group. So they observed forbidden photofragmentation via the M1 and E2 mechanism. And you see that agreement between theory and experiment is perfect. Then, well, they of course observed also the dipole allowed transitions. And you see that, well, the agreement between the semi-classical and quantum mechanical model is quite erratic. In many cases, in most of the cases, there is no agreement. In some cases, with these green dots, there is a decent agreement. Well, in some cases, we could get the agreement by refitting the experimental, the theoretical expression to the experimental data. Okay, I have 2 minutes left, so I will tell you what are our future plans about strontium molecules. And the future plan is to look for gravity with molecules. Well, there is a conjecture that actually there is a correction to the Newton gravitational law, which is of Yukawa mathematical form. And the question is whether very high precision molecular spectroscopy experiment can tell us something about this additional term. So what we have to do is, of course, we have to go beyond the Born-Oppenheimer approximation. We have to include the adiabatic, which is proportional to the ratio of electron to the proton mass, then non-adiabatic, which is proportional to the square, then relativistic and QED, which is alpha square mu and alpha cube mu, and finite nuclear size. Now, of course, the accuracy of the ab initio calculations is not sufficient to guide this experiment, but very fortunately, we have only 5 mu-dependent terms and 6 isotopic combinations, which means that we can use 5 isotopolog to fit 5 terms to the experimental data, and then use the 6 to measure deviations of the energy levels. Now, we know from theory that if the deviations are inversely proportional to the interatomic distance, this is due to QED. If they are exponential in R, this is due to the 5th force. Now, let me stress you that this is a very challenging project just because nobody computed thus far the terms that are proportional to alpha square mu and alpha cube mu. And alpha to the 4th mu is even not defined by theory. So this is my last slide. So this is in yellow, this is the present knowledge about gravity correction to the Newton law. This is a prediction from electroweak scale light boson, and we hope that the ground state spectroscopy of the strontium molecule will just join the 2 regions. And with this last slide, I thank you for your attention.
Thanks for sharing great results. Due to the time limit, we will have very short questions. If not, let me ask one short questions. So can you give any comments on the future applications? So can you do the quantum control between the bound states and the final continuum states? Because your photo association seems very nice tool to control all your states.
You mean I didn't quite get...
So my question is, for instance, if you control the field, the external field, to control the final continuum states, it seems like you're.
You mean in the photofragmentation experiment, there's a very weak magnetic field which is very well controlled, and this is how they can experimentally they can pre-select the Zeeman sublevels.
Any other questions? Okay, and let's thanks again, and let's move on to the second speaker. So the second speaker is Professor Jing Zhang from Shanxi University in China. So he'll talk about his recent result on spin-orbit coupling in a Fermi gas.